series turns a transcendental function or others into a polynomial. What's a transcendental function? E to the x, sine x, cosine x, e to the x, logs, trigonometric functions, hyperbolic functions. Those are transcendental functions. And others would be messy square roots. How about that? That's the other. And it turns them into a polynomial function. And the reason that's nice is because it's going to look like a power series, which means we can take derivatives of it, we can integrate it, we can do all kinds of nice things with it once we get it in a polynomial form. And the exclamation point in the middle of the sentence means that the approximation is very close around a given point. Do you remember the graph I showed you the other day where it wanders off if it's not around a given point? But all you do then is just move your point over. So a Taylor series about means around, about a point A is, and they start them at 0 in this book, the sum as n equals 0 to infinity of, maybe using K, I'm trying to do it the way they do it. There's a whole bunch of different ways of writing these. Let's see. So I need to move. I'm sorry, but this is going to be, until we get this fixed, it's going to be a nightmare. So may as well take a minute and fix it. Ooh, that is worse. Now that's better. I'm drawing a line and then I'm trying to draw a line over it. That helps some. I think that'll get it. Too high. Aha. I'm getting tired of that. The They play videos on this thing in the night classes and reset the auxiliary card, the video card for the videos, and that's what our problem is. It's a series about a point A that approximates a given function f of x by taking derivatives of that given function. And the idea is, what you learn quickly in Cal 2 is, it's a whole lot easier to take derivatives than it is to integrate. So we take derivatives of it and make a polynomial out of it. And then obviously, the more terms in the series, the better it is. We saw that, didn't we, in our study of infinite series? And that is, if I'm in a hurry and don't want to do but say 4 terms, I'll get a pretty good approximation. But if I added 4 terms, I would get a good approximation. If I added 4 more, I'd get a very good approximation. Okay? And I'll show you about that in a minute. Let's see. That's about it. It's time to use it. So let's start with 1. Let's see. Let's start with 1. Let's do, this is example 1 on page 603. I want a Taylor series for 1 over x for f of x equal 1 over x at a equal 2. Okay? So I know then that that f of x is going to approximately be equal to the limit from k equals 1 to infinity, k equals 0 to infinity, of the kth derivative of f of x over k factorial times x minus a. That's what goes on your card. Okay? So in our case, that means that if f of x is equal to 1 over x, I need some derivatives. Did it say how far to carry it? No. So this is x to the minus 1, right? So f prime of x is equal to minus x to the minus 2. Is that right? And f double prime of x is equal to 2x to the minus 3. And f triple prime of x is equal to 6x to the minus 4, and so on. I need those derivatives because of this. You've seen that before, haven't you? Haven't you seen that? And what this means is, just so there's no doubt, this means that's what it means. That means whatever number is in parentheses up there, called a superscript, it means take that many derivatives. So if I wanted, what do you think that is?
Function to the x?
No, look how high it is. Reason you don't know is you've never seen it before, because that is x in Roman numerals is 10, right? You remember that? And that says take 10 derivatives of f. You follow? Well, you'd get tired of Roman numerals after. Have you ever seen, a lot of times on movies, at the beginning or end of a movie, they list the year it was made in Roman numerals? Have you ever noticed that? And we'd get tired of that in a hurry, huh? So all we're saying is if I put a superscript, if I didn't have the superscript, that would mean f squared, wouldn't it? Do you agree? But in parentheses, that means take that many derivatives. Okay? And that keeps all of us from having to have a quick review in Roman numerals. Okay? So now, take that one off. So now, our f of x is 1 over x, and it is equal to then k equals 0. That is the 0th derivative of f. What if that even sounds strange? What's the 0th derivative? Doesn't that mean don't take a derivative? Everybody agree? So wouldn't that just be f of 2, and that should be a, shouldn't it? F of 2 divided by 0 factorial times x minus 2. Everybody agree? All I did was let k equal 0. Okay? Now that's plus. Now k is equal to 1. So isn't that the first derivative of evaluated at 2 over 1 factorial times x minus 2. Follow what I'm doing? And then plus. Now, that was k equals 0. This is k equal 1. Now I do k equal 2. K equal 2 means the second derivative, doesn't it? At 2 over 2 factorial times x minus 2. Everybody agree? And just so there's no doubt, that 2 comes from right there, and that 2 comes from right there. This one comes from whatever k is.
And there's not a, that, just for the formula, is it's not a 2 there above the FK? Is it an A there, or is it a 2?
That is f sub k of, and it really should have an A, huh? Right there. So do you see where everything comes from? Everybody? Okay. Now, then this is, then one more is plus f triple prime evaluated at 2 over 3 factorial times x minus 2. And I'll need one more derivative then.
Shouldn't that 6 be negative anyway?
Do what?
Shouldn't the 6 be negative?
Yeah, this,
Every other one's negative, yes. Thank you. So now I substitute in, right? So that is equal to x. The first one is just f evaluated at 2, right? So let's see if I have room to write them. F of 2 is equal to 1/2. Do you agree? Put 2 in the place of x here. Don't you have to put 2 in the place of x there? F prime of 2 is equal to minus 1/4. Look, put 2 right there and put 2 over here. F double prime of 2 is equal to minus 1/8. plus 1/8? Y'all tell me when, I'm gonna guess a while and y'all tell me. F prime of 2 is 2/8. I was looking at the wrong line. 2/8, how about that? And F triple prime of 2 is equal to, let's see, wait a minute, yeah, there's prime, double prime, triple prime, and this is the fourth derivative that I'm not going to use, is equal to minus 6 over 16, is that right? And that's enough for what we're doing. Do you see where the numbers come from, everybody? So now I have f of 2 is 1/2 divided by 1 times x minus 2 plus f prime of 2 is minus 1/4 divided by 1 times x minus 2. F double prime is equal to plus is 1/4 divided by 2 times x minus 2. And then F triple prime is plus a minus 3/8 divided by 6 times x minus 2. Yes, what did I do, Byron?
In the book on the formula, it has the x minus a to the k power.
Right. And it's right. Thank you. So this is to the 0 power, to the 1 power, to the 2 power, and to the 3 power. I'm going to just pick one and draw an arrow. So this is 0, 1, 2, and 3. I'll let that off right there too. Okay? Everybody? Now what? Well, I think this is equal to, is that 1/2?
0 factorial?
What?
What is 0 factorial?
1.
It
It's
is?
just one.
Yeah, I bet that's one of those things that mathematicians do. When we had to give 0 a meaning, because 0 factorial a meaning. Why? Because it comes up in problems, right? And naturally, you and I would think that means start at 0 and go to 0, which would mean it is 0. But then every time you divide by a factorial, you get 0, because you're multiplying 0 times a string. So in order to make it work, it is defined to be 1. And defined to be means we had to call it something, and we picked something convenient. Okay? So that's why you've got these two ones in a row. This is 0 factorial, and this is 1 factorial. Okay? Now that's looking like minus 1/4 times x minus 2. And this is looking like plus 1/8 times x minus 2 squared.
1/4.
What's wrong?
1/4.
1/2 of 1/4.
Okay, I got you.
And this is looking like plus a minus 1/16 times x minus 2 to the third. Is that true? If you take that 6 and you multiply this by 1/6, then isn't it easy to see the minus 1/16? Everybody agree? So what I'm telling you is that 1 over x is what's that symbol mean? Approximately equal. And also what I'm telling you is you can get that number as close to the real number as you want it to be by adding terms out there. But for right now, let's just take our simple approximation. And let's say I want to find f of 2.1. Remember, I have to stay close to 2, don't I? Everybody agree? So doesn't that give me, and watch the guy that hates decimals. Is that right? Everybody? Somebody do that for me on a calculator. I can make it a little easier for you by writing it as this. What do you get?
4761875.
Let's see. Point
4762.
476.
47.
Oh, 47. Go ahead.
2.
Give me one more if you got it.
47619.
Okay. William, you get that?
I'll tell you here in just 1 minute.
Okay. Now, that is our approximation, right? But in this case, we know the real answer, don't we? The real answer exactly is f of 2.1 is equal to 1 over 2.1. Isn't that right? And what is that?
10 over 21.
Give me a decimal, please.
0.4761904.
0.47619.
Mine's 875, but same numbers until then.
I think it's got to be less than a half, because 1/2 is 0.5, right? And remember what we were doing with series, the denominator is larger, therefore the whole fraction is lower, right? So it's got to be not too much lower than 1/2, 0.5. So I suspect that number looks better. It wouldn't be anything over 0.5. You want me to come look at it and see?
Yeah, I was able to get it. I was pushing some wrong buttons, but.
The calculator's converting this to exponentials.
Yeah, it did on that, just that last term it did. Because it was to the -5, I don't know.
Yeah, you're okay. You got that. You're okay. Okay. So do you get what we're doing? Now, these two, this is 100% correct. This is the Taylor series approximation. And I knew they were going to be close. But they're not close enough, are they? So what's the solution? More terms. Everybody agree? More terms. So just keep going. Okay? Now, you're going to have instances where you don't know the number, right? In that case, you're going to do as many terms as you can stand to do. And you know what's one of the best things to do a Taylor series on is a spreadsheet. Spreadsheet's a wonderful thing to do a Taylor series on, because you can make a column with the K's in it, and just put that into the spreadsheet using a calculation button. And then you can do a running total, can't you? Now, let me ask you this. Here's my way of telling when to stop. I know they're more high-class ways. But let's say that I know that, let's say that 4.619 is the right number, which it is. And suppose I have on a spreadsheet K, and then suppose I have A sub n And then suppose I have S sub n. So if k equals 0, my a sub n is going to be 0.5. Isn't that the first term when I substitute it in? With a equal 2 and f of x equal 1 over x, and we want to find an approximation for f of 2. Then this first sum is 0.5. Do you agree? Now if k is 1, that is 0.025, right? Subtract it, right? So that's 0.5, so this is 0.025, which is 0.4 4975. Y'all check me. What I'm trying to do is I'm trying to subtract that.
475.
I'm trying to subtract this from this. And didn't I knock off 0.25 way out there? No. Let's see. Tell me what that is. That's a,
475.
am I off a decimal?
Yeah.
So it's 0.475. Is that right? Okay. Do you see how I'm closing in on it? Now, with k equal 3, with k equal 2, the next term there is equal to a plus 0.00125. Is that right? I'm dividing it, I'm multiplying it by that, and don't I move my decimal point over 2 more? Oh, I'm here.
Just one 0.
No, I think it's 2, isn't it? I'll have to have 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 4, 5. I'm right, huh?
Yeah.
So now I add this number to this number. What do you get? 0.47625.
Yeah,
Is that right?
that's right.
Well, that hurt us more than helped us, didn't it? Now the next one is a 3, and that is 625 with 1, 2, 3, 4, 5, 6, 7. So I need 4 zeros. And that'll just affect this last term.
So subtract that from the.
Yeah. Is that right?
476. I got 18.
1/8, okay. And wait a minute. The first 4 places stay the same.
Well, we used to
No, the first 3 stay the same, and then it goes down, okay. Okay. Four, 7, 6, 4, 7, 6, 1, 8. See how we're closing in? Everybody see what we're doing? So, if I go down to say, if I wanted to see how far I have to go, suppose that I had at k equal 20. Suppose that I had at k equal 20, and suppose I had 0.4, 6, 1, 9, 9. I'm making this up. Understand? And then suppose at 21, and suppose then I did 21, and I got something here, and you could get something there on your calculator, couldn't you? And suppose this changed to 0.4619. It's going to move slowly, isn't it? But doesn't that tell you if these two are no longer changing? If those two are no longer changing, doesn't it tell you that our approximation is accurate that far out? Everybody follow what I'm saying? So that's how you know how far to go. The book does it the way I did it in 1967 in Calculus 1, and it doesn't have to be that way. Nowadays with a spreadsheet, you can just put in a value of k, or even with your calculator, you can put in a value of k, and you'll be able to get the sum, and then you will know whether to keep going or not. Follow? And that's done with an Excel spreadsheet. And if you don't have Excel on your computer, there's a free application called, anybody a computer techie? Libre what? LibreOffice, which will look so much like Excel, you and I can't tell the difference. And it's free. So that's the power of technology now. And you do a copy and a paste, and what you do is I can tell that X column, that K column over there, I can tell it to add 1 every time, and I can do a copy and paste, and by the time I hit the enter button, I can have 100 terms, and the sum at 100 terms. In 1967, we didn't even have calculators. We didn't have add, subtract, multiply.
This thing sent us to the moon, didn't it?
Huh?
Something about smart as this sent us to the moon.
Yeah. We had an IBM 1130 computer and had just gotten a Fortran compiler, and you had to go write a program to do that. And it was a big deal. I mean, it is cause for celebration. And if you needed to make your N bigger, you had to change the program. So, can I leave it like that? that in a real world application, you'd use something like a spreadsheet, and you would know, depending on how much accuracy you want, how big to make in. Everybody agree? Okay. I'm not going to ask you to find in on the test. There's a section in here that does, but I'm not going to go back to the Stone Age when I got Goodyear tires to ride on. Okay? Any questions? Any questions? Oh, there is one thing though, and that is this. Suppose that I wanted to write that I wanted to write 1 over x as the sum from k equal 0 to infinity, and write it in sum notation. First thing is, and what I'm looking at is this line right here. And this is k equals 0, k equal 1, k equal 2, k equal 3. Do we agree? So first thing is, do you notice it's an alternating series? And you remember how we make an alternating series, don't you? And that is, this is minus 1 to the k. Doesn't that make it an alternating series? And it's either k or k plus 1. And the way you know whether to add a plus 1 is, the first term is positive. The 0 term is positive. So if you put 0 in, you get a positive number, don't you? So that's how I know. Now I've got the signs taken care of, right? And then I know it's pretty easy to tell that I've got x minus 2 to the k. Isn't that pretty easy? 0, 1, 2, 3. Then the question is, what's going on here with the numbers? That's always the hardest. That's always the hardest. If you look at just the numbers itself, what's happening? Can you say geometric series? Aren't you in every term multiplied by 1/2 to get the number in the next term?
What about like the x or the minus 2?
The x minus 2 I took care of right here. I took care of the alternating sign. I took care of the x minus 2. But now I've got to do something to say that it goes from 2 to 4 to 8 to 16. So I'm going to have 1 over something. What's the something?
2.
2 to the what power? Well, let's see. In the first term, with k equals 0, I get 1 over 2, right? With k equal 1, I get 1 over 4. with K equal 2, I get 1 over 8. So is that
4.
2 to the I'm not going to use negative exponent. Is that 1/2 to the K plus 1 power? Is that the way you do it? Everybody? So do you see how I did it in 3 parts? I did the SIGN, then I did the X term. I looked at the values of K and figured out what to put for the X term. And then I always take care of the numbers last because they're always the hardest. And this one wasn't particularly hard, but as Madison says, my granddaughter, it makes my brain tired. She says math makes her brain tired. I bet there are a lot of people in Math 97 on this campus that would say the same thing. I bet. Everybody see how I got that? And did you notice there wasn't any formula, nor was it particularly an act of brilliance? It was just an act of looking at what the K's is for each part, one at a time, to decide what it is, huh? Okay? So now I need to know now let's be clear. All of that work over there on the board has to do with how big an N do we use, right? Is that correct? Now what I'm asking is, how far can I get away from 2 and still have an approximation? Do you remember a Taylor series? It uses the word about, meaning around. And that means you got to stay close to 2, huh? But close to 2, close might mean one thing if I'm whispering in your ear, and it might be another thing if I'm lobbing hand grenades. So we've got to now define the interval of convergence, which says how close do I have to stay to 2 before I rewrite the series with, say, A equal 3. If I get too far away from 2, it's going to quit being a good series, and then I'll just move over and make me a new series. Okay? Everybody follow? I'm not giving it to you in precise mathematical terms. I'm trying to give it to you in something that makes sense, huh? Okay? So, here's what we're going to do. We're going to use let's see. I hadn't used this baby in a while. And as my other granddaughter, age 2, would say, yay! Now we got us a clean page. How do you determine where that series converges? Which test?
Geometric series test.
Hey, that's not a bad idea. That's not a bad idea. I think I'm gonna use something that has an absolute value in it. Why? Because I want that -1 to go away. Does that make sense to you? So, in honor, no, to heck with Dr. Thomas. No, not to do him that way. In honor of me, we'll use the ratio test. He would use the root test in a skinny minute. The ratio test says that I want to look at the absolute value of a sub n plus 1 over a sub n. I'm going to construct that first, and then I'm going to take the limit of what I get, right? So once I do absolute values, do you agree the -1's gone? So now I've got 1/2 to the k plus 2 to the n plus 2. I switch to n's. To the n plus 2 times x minus 2 to the n plus 1. Right? Oh, here he comes. He's going to get on me now. Everybody agree? Over 1/2 to the n plus 1 times x minus 2 to the n. Isn't that the way we do it? I just got through telling them I have to do this before Dr. Thomas gets here. Why?
I'll try to do the root test.
Exactly. Not try to. That's a beautiful one. Everything is raised to a power. Huh?
Yeah.
So isn't that screaming root test at your head?
Right.
Of course, to me, it is screaming ratio test.
Okay.
And the two they're almost always interchangeable, aren't they?
Except when you have factorial.
That's right. That's right. Okay. So I think if I divide those two, what do I get?
One.
1/2. Everybody agree? Wouldn't I have somewhere over here 1/2 to the n plus 1 minus n plus 1, and that's a 2. Don't you subtract the exponents when you divide? And the n's go away, and don't you have 2 minus 1, which is 1/2 to the 1? Okay, so there's 1/2. Here I have x minus 2 to the n times x minus 2 to the 1. Do you agree? Isn't that what x to the n plus 1 is? And those two divide out. So I have then 1/2 times x minus 2. Everybody? Okay. Now, here's what Dr. Thomas would tell me. He would say, Miles, if you had just used the root test, you would take the nth root of that which is, the nth, which would make that just be 1, right?
Would it not go over all those? Would it?
Remember, it's in absolute values, right? So I can throw that -1 away. Right.
Would it be K plus 1 over K?
It'd be, it would be, the root test would be, Ed, watch me and help me on this. The root test would be, the root test says take the nth root of a sub n. And in absolute values at that. Don't I remember? The absolute values is going to make the -1 go away. So now I have, then, I'll have, that's equal to, and a sub n is equal to 1/2 times 1/2 to the n times x minus 2 to the n. Agreed? Ed, do you see what's about to happen?
You got 1/2 to fix those.
I get 1/2 to the 1 over n power. I think what's going to happen is I'm going to take the nth root of all of this. I don't need to worry about, well,
And if the nth root though?
yeah. So now I get 1 over 2 to the 1 over n power. 1 over 2 to the 1 over n power. Isn't that right?
We'll do that 1/2.
Times 1/2 times x minus 2. That's what does it, Ed.
Okay.
Then I take,
No, the limit, yeah.
then I take the limit as n goes to infinity,
Okay.
and I have 1 over 1. If I take the limit of this, now I take the limit as n approaches infinity of and that is equal to 1 over 2 to the 1 over infinity power times 1/2 times x minus 2. But what's 1 over infinity? 0. That becomes 0. So don't I have 1/2 times x minus 2? Everybody agree?
Yep.
Everybody? Okay. All my n's are gone here, right? In mine and in that one. So when I take the limit of this as n approaches infinity, if there are no n's in there, isn't it that? Everybody agree? Okay? Now what?
Are we doing the Taylor series here, or are we just?
I need to find the radius of convergence. And I also need to put that back in, because I had it here. Do we agree with that?
Why would you exclude the 1/2?
Well, the absolute value of 1/2 is,
1/2.
that's why I did.
Okay.
Very good question, though. But for it to converge, the limit has to be equal, has to be less than 1, right? Isn't that what the ratio test says? Agreed? So I want 1/2 times x minus 2 to be less than 1. Is that right? So x minus 2 has to be less than 1 and greater than minus 1. Do we agree? And x has to be between 3 and 1.
What happened to the half there?
Yeah, aren't you
did we
supposed
skip
to-
something?
That should have been a 2.
Oh, okay.
Yeah, we forgot something. So now that's 4 and 0.
You know what that's similar to? In Calculus 1, when you're trying to prove the definition of a limit, it's the same kind of math.
That's exactly right. This is the delta calculation of that. And this, each of these would be plus or minus epsilon. You're exactly right. So what we're saying is, now I know the series, don't I? On the previous page, I've got it marked in purple. That purple box. Now we know the series. And through this table, we know how big to make n, right? And now I know what values of x I can tell people that series will work for. And those are the 3 parts. Now let me ask you this. Does the value of x, think on this before you answer me, does the value of x, how far it is away from 2, would that affect n? Yes or no? What? Travis?
I don't think so.
I'm thinking about it myself, Travis. That's why I didn't say anything one way or the other. I'm thinking it does. Here's why. I'm thinking the further I get away from A, which is my real point that I know, right? I think the worse my approximation gets. Right? And therefore, if I want to have 4 digits out here, I might have to go to 100 before I can get 4 digits. Because I might have to add more terms to make up for the distance from A. That's my thought, Travis, but I hadn't done it in a long time. When I have time, I am going to do it, though. But for right now, that's my thought. Okay? What I want to show you is this. This is page 605. is for the function, this is for the function y equal cosine x. And it is in light blue. That would be that line right there. Does that look like the cosine with the humps in it?
Mm-hmm.
And notice with an x value of 3.14, that's about where that yellow line is. With an x value of 3.14, notice that the y value is 0. And is it supposed to be? No, it's supposed to be 1. There is 3.1. This would be 3.14. And the cosine of pi is, the cosine of pi, which would be 3.14, is -1. And there is the point on the blue line, on the blue curve. Does everybody see it? So here's what we did. What we did is we did the same thing I just did with my example. We built Taylor polynomials with n equal 0, 2, 4, 6, 8, 10, 12, 14, 16, and 18 terms. Isn't that 18 lines in this table? Does everybody follow? And then those polynomials, you remember the one I had in blue in the box? Those polynomials, we graphed them. You get the idea? And what this shows you is the right graph is blue. At p equals 0, that means just one term, you get a straight line. That's no good. At p equal 2, isn't that, at p equal 2, isn't that a parabola or the makings of one?
What kind of line is that? It's not a tangent line, is it?
Say what now?
Like what is it?
What
Is this
I'm
just that's how
trying to
accurate it
do
is?
I'm trying to use polynomials like the one we made a minute ago for 1 over x I want them to be as close to this graph as I can. And what I'm trying to show you is that the more terms you put in the polynomial, the better it is. So if I have n equals 0 has 1 term, n equal 2 has 3 terms in it, 0, 1, and 2, right? And the second term will have an x squared in it, so it's going to look like a polynomial. Everybody agree? So n equal 4, n equal 4 will have an x to the 4th term in it, and n equal 4 is this purple line, and that purple line goes right along with, I'm sorry, that's n equal 8, has that purple line right along with it. Do you see that? So it's good, n equal 8 is good from here back to here. But then n equal 12, look how good n equal 12 is. n equal 12 sits right on top of the blue line from x equals 0 to x equal to about 4 3/4. Do you follow? And that goes with the more terms we put in the polynomial, the better the approximation is. Yes.
Well, the graphing calculator is a great use to check your work.
Yeah, it is, because you can graph the polynomial you approximated by, and then graph the function itself. Everybody understand?
Keeps from making, if you have an error, it'll show up.
Look out here at n equal 18. N equal 18 is this green line. And notice this green line goes all the way out to about there before it wanders off. So does everybody follow what I'm saying? So the higher the n, the better the approximation. The closer you are to the original value A, the better the approximation. And the way you tell how good your approximation is build a table like this using a computer. Any questions? Any questions? That's a Taylor series. And to find the radius of convergence,